Good morning. I'm Dexter Locke. I'm a research geographer at the USDA Forest Service Northern Research Station located in the Baltimore Field Station. It's an honor and a privilege to be asked to speak here. Thanks to the Florida Urban Forestry Council and the Urban Forestry Institute for the invitation. And I hope you'll find today's presentation useful. I was asked to talk about urban forestry, environmental justice, and redlining, so I'll just jump right in. So when I look at the environmental justice research, I categorize it into these four boxes, this 2x2 table. A lot of the research I've seen in the top is looking at patterns. So who lives near environmental disamenities like airports, locally unwanted land uses like incinerators and heavy industry, or who lives near tree canopy and parks, environmental amenities. On the bottom, it tends to be more qualitative research focusing on the procedures or processes that led to those land use decisions. So these are historians, legal scholars, anthropologists looking at who's at the meeting, how are the power structures organized that led to those processes. So I find most environmental justice research is somewhere along this pattern, process, amenity, disamenity, both of those spectrums, and this is a crude way to categorize them. In practice, most research tends to blend these. I offer this as background because today I'm going to be talking about environmental amenities, tree canopy, and patterns, who lives near high tree canopy cover and who does not. So a little bit of background on the homeowners loan corporation and redlining. So as part of the New Deal, the Homeowners Loan Corporation worked with realtors across the country to categorize neighborhoods for safest to invest and riskiest to invest. And the idea was coming out of the Great Depression to protect homeowners at risk of foreclosure and the economic consequences that would come from that. And so the idea was to determine where the federal government could direct mortgage assistance. So far, so good. From a research perspective, redlining has a lot of attributes that make it very helpful for research. It was consistent. It was racial, which we'll get into in a moment. It's spatial, so it's on the map. Neighborhoods were literally categorized on different maps in A, B, C, or D. And through the magic of geographic information systems, we can overlay that with other important data and information. It was applied at the same time, so in the mid to late 1930s, and the 239 largest metropolitan areas were all categorized. So it has some great properties to help us understand things today. I mentioned it's racial, so quoting from the Homeowners Loan Corporation appraisal of this neighborhood here in Baltimore City, where I do a lot of my research, in the description, it says an old residential section seriously threatened with Negro encroachments. A small section along Reisterstown Road consists of fairly modern two-story brick rows, that's short for row homes or townhomes, mixed. Some Negroes, some owners of long-standing, still occupying old residences, and it goes on. So those are their words, not mine. Quoting from the description, you can see that it's a mix of age and recency of housing stock, the occupation and racial composition of who lives there. Later, it describes favorable features, Druid Hill Park, which was designed by Frederick Law Olmsted, and good transportation, detrimental features, obsolescence. So you can see it was a mix of characteristics that define these different neighborhoods. Some national numbers from 1935 to 1950, 2.75 million loans were insured by the Federal Housing Administration. Less than 2% of those went to African Americans, about half of which were through a special military program. And at the time, African Americans represented about 10% of the US population. So if you were Black or African American, your odds of receiving this type of mortgage and mortgage insurance was 1/5 the probability of your white counterparts. Looking in Baltimore City, where again, I do a lot of my research, we have about 15,000 vacant homes, about 15,000 vacant lots. Both of those numbers are moving targets. On the right, you can see those vacant lots and vacant buildings overlaid in a map of redlining. And what you can see is a very clear correspondence of the preponderance of vacancy today with what was formerly redlined 80 years ago. And so a lot of research has looked at redlining and social outcomes like poverty and unemployment. We see low educational attainment and poor health and what used to be systematically disinvested in. And the literature has now matured to the point where we have social determinants of health meta-analyses looking at all the research on redlining and social outcomes today. But what about trees? What about environmental things? I don't need to tell this group about the benefits of trees, especially in urban areas. But we know that there's health benefits, reducing the urban heat island, increasing property values, reducing stress, managing stormwater, and so on. So I was curious, along with my colleagues, to understand, what about redlining and environmental things? So again, trees provide environmental and social benefits in urban areas. For example, it makes it cooler in the summer. Heat islands disproportionately affect vulnerable populations. So we reasoned if larger single-family detached homes, those A-graded neighborhoods, would have more space for trees, then we would see more tree canopy today. Another plausible mechanism would be A-graded neighborhoods might have more access to power and would be more likely to get parks and open space, tree canopy through street trees in their neighborhoods. Then we would see more tree canopy today. So multiple pathways to the same outcome that would explain more tree canopy in A than in their D graded counterparts today. So we downloaded data from the University of Richmond, who has generously made available redlining data. They've geo-rectified and digitized a bunch of data throughout the US. Here's a collection of maps through in Southern California. This is in Los Angeles. And you can see they give you the breakdown of the different neighborhoods, demographics, and so on. It's a great resource. So we looked at 37 cities for which we had high resolution tree canopy data that were also redlined. And to the left of the dotted line, we had enough data to look within the cities, but for all the cities, we could compare across cities A to B to C to D. And so you can see the 37 cities that were included and the number of neighborhoods according to the Homeowners Loan Corporation classification system. High resolution tree canopy is probably familiar for many in this audience, but what we're doing is defining the earth from above into these land cover types. And we're particularly interested in tree canopy. This happens to be a 9-inch resolution map for Los Angeles County. How does it work? Passive sensors, such as imagery, basically cameras. This is looking in New York City. The tree canopy on the right is in Central Park. We have shadows. A lot of urban canyons are obscuring trees. Using an active sensor called LiDAR, light detection and ranging, we can actually see through the shadows, focusing on the same area, emitting its own light source. LiDAR returns a very detailed image, very detailed data, which are latitude, longitude, and elevation, so X, Y, Z points with their intensity. And we can see through the shadows and pick up trees that would otherwise be missing. So we get these very detailed point clouds. Again, this is the southwest corner of Central Park, and you can see it becomes easy to extract tree canopy in a way that would be difficult with imagery alone. This was developed by the University of Vermont, who's created tree canopy and land cover maps across North America and is an industry leader. So imagery, false color, the height of features relative to the ground using LiDAR and imagery fused to get candidate trees, And the expert rule system iteratively develops the other land cover classes. So we summarize the tree canopy within these redlining polygons, A, B, C, and D across 37 cities. Our first model says, are there differences from A to B to C? Yes. The second model says, are there differences by city? Yes. Why would we expect the same tree canopy in Tampa and in Seattle? And then the third model combines the across city variation with the A to B to C variation. I want you to focus on model 3. So what we see is, on average, formerly A-graded neighborhoods have 43% tree canopy cover today. And the formerly D-graded neighborhoods have about 23% tree canopy, or 21% less tree canopy. So imagine it's a rainy day and you have 43% of an umbrella, and then it's a rainy day and you have 23% of an umbrella. It's not only a statistically significant difference as shown here in the table, it's a meaningful difference. In the Mid-Atlantic, where I do a lot of my research, we know that 40% tree canopy is an important threshold as watersheds urbanize. Below that 40% tree canopy cover, we see a lot of damage to our watersheds in terms of water quality. So 40% tree canopy cover is an important threshold. Research in Madison, Wisconsin shows that 40% tree canopy cover is an important threshold for the cooling benefits and urban heat island mitigation of tree canopy. And then many municipalities have canopy goals. Washington, D.C. has a 40% goal. Baltimore City has a 40% goal. Philadelphia is 30% per neighborhood to have that canopy more equitably distributed. So those areas that were single-family US-born white households in the mid to late 1930s meet or exceed that important policy and biophysical threshold. Whereas immigrant communities, communities of color, 80 years ago, those neighborhoods today are below that important threshold for receiving the benefits of tree canopy. Let's zoom into the 10 largest cities where we have statistical power to look at the patterns there. And what we see is, in every case, A-graded neighborhoods have statistically significantly more tree canopy cover than their D counterparts. In Seattle, there's a couple of aberrant neighborhoods. Those are formerly industrial areas, shipping areas that have become large waterfront public spaces and parks. So they have a lot of tree canopy today. I'm speaking to a group of people in Florida. I'd be remiss if I didn't include Florida. So here's the data we had for Tampa. A and B are not different. A and C are not different, but A and D are different. This is underpowered. This is why in the main analysis, we did not include all the cities, only large cities. In some ways, this is a foregone conclusion. But you can see the trend, even if we don't have enough data, that A, B, and C are greater than D, although we really don't have enough data to drill down. And I should mention that Sean Landry has been a real leader for the last 10 or 15 years in urban tree canopy mapping, in Tampa in particular, but in Florida in general. And he's produced a lot of great data on tree canopy. We tried to stress test our data. Were the results because of the largest cities and the patterns there? So the purple removes the biggest metros. What about where we have some partially missing data in some of the suburban area? We're missing 2% of the polygons in Detroit, for example, because our tree canopy map today doesn't cover the extent of the redlining 80 years ago. What about if we think about New York City as one unit or as 5 boroughs? Similarly, Boston as multiple municipalities or one large area. What about the data source? Most of our data came from the University of Vermont Spatial Analysis Lab. What about if we exclude data from other providers? And in all those kinds of tests, what we found was the same thing. Redlined areas have about half the tree canopy cover as their A-graded counterparts today. No matter how hard we tried to see if it was a statistical or methodological artifact, the main results were very clear, stark, and they persisted. So in summary, we know that trees provide a lot of social and environmental benefits, especially in urban areas. Some qualitative research, legal scholars, anthropologists, and more in Baltimore have looked at redlining and how it's played a causal role in the location and allocation of trees. We wanted to see if those patterns were consistent in other cities and if that's scaled up. Overwhelmingly, yes, we see A, then B, then C, then D. The rank order of the real estate appraisal system 80 years ago, which was race-based in part, mirrors the distribution of tree canopy today. So we invite additional research to examine the processes of explaining the location and allocation of trees in other cities, and we've made all the underlying data freely available for others to build upon. Two other research teams have conducted similar research using coarser resolution tree canopy data. And so instead of 43% tree canopy cover in A and 21% tree canopy cover in D, they find about 20 and 11 on the left. And then also research by another team linking tree canopy, redlining, and heat data show that the land surface temperature is significantly greater where we have less tree canopy in areas that used to be graded D relative to their A counterparts. So again, going back to the southwest corner of Central Park, here's the imagery. Those other two teams I just mentioned were using Landsat. It's a coarser sensor. It's a passive sensor, so it doesn't pick up all the tree canopy that our LiDAR-derived estimates could find. Nevertheless, 3 research teams, 3 different data sets, same overall finding. A, B, C, D, the rank order of redlining matches the rank order of tree canopy today. So a really thought-provoking paper by Chris Schell and colleagues in Science that came out and said, well, if the spatial distribution of tree canopy in parks reflects the legacies of redlining, and if vegetation in urban areas is the base of the food web, might we have entirely different ecologies based on the vegetation, because insects live on trees and birds eat insects, and if the vegetation is different, we might have entirely different urban ecosystems today. So a number of research teams are actively pursuing these kinds of questions based on the redlining data, tree canopy, and urban conservation ecology. The world is more complicated than just 3 variables, right? The world is more complicated than tree canopy, redlining, and cities. So it's important that we realize it's a multi-causal world, and the iterative process of researching, looking at pattern, process, pattern, and the underlying processes that created those. So this is by no means the whole story, but I just wanted to share how redlining is a strong predictor of tree canopy today. I'm going to pivot slightly to some research on street trees. Street trees are really important, a really important part of the urban forest, even though most of the urban tree canopy research using high resolution tree canopy maps shows that most of the land in urban areas is residential, most of the tree canopy is on private residential, and most of the opportunities for additional greening are also on private residential. Street trees play a unique role because it's part of the urban forest that most people have a lot of access and contact with. I love the nature pyramid here. It's kind of like the USDA food pyramid with carbs at the bottom, working all the way up to salts and sugars, more sparing at the top. On the left of the pyramid, we have spatial scales, so neighborhoods, regions, and then up to national and international. And on the right side of the pyramid, we have a temporal scale. So we might have daily contact with neighborhoods, weekly contact with more regional parks and open spaces, maybe monthly visits to national parks, and then maybe rare international trips, once-in-a-lifetime opportunities. So street trees occupy this space at the bottom, excuse me, of this frequent neighborhood daily contact. And also in most municipalities, it's one or very few actors involved, as opposed to New York City, which has 750,000 private residential landowners or private forest owners, or about 250,000 private forest owners in Baltimore City, a lot of residential land. And each residential landowner has different motivations, capacities, and interests. So street trees are really unique in that we have one or a couple of actors, and they have very frequent neighborhood contacts. In Baltimore, looking at the redlining map, we now have a full street tree census carried out by the Davie Resources Group, shown on the right, served to the city on an interactive web map. We drilled down into the neighborhoods, and we wanted to make sure we were sampling comparable areas. So we created these hexagons, this kind of honeycomb pattern. And on the bottom right, you can see the location of the street trees and trees in managed areas of parks. So we wanted to know how the street tree population today varied by redlining categories. We used a species accumulation curve as a way to look at species diversity. And briefly, we marched through the data set, and let's say we go red maple, red oak. So we've got 3 species along the, 3 trees along the horizontal, but only 2 species along the vertical. And we keep sampling through the data set, and we see how many trees do we have and how many species have we accumulated. And when that becomes horizontal or near horizontal, we know that we've sampled all the possible species we would expect in a natural ecosystem. And what we see is that A and B areas have significantly greater species diversity today than their C and D counterparts. And we know that species diversity is important for resilience. The next urban forest pathogen can move unchecked from tree to tree to tree if they're all from the same species. We've seen that with Dutch elm's disease. We've seen that with emerald ash borer, Asian longhorn beetle, and so on and so forth. So species diversity, as we know, is important for resilience. And what we're seeing is, from the previous research, not only do degraded neighborhoods have less tree canopy, but their street tree communities are significantly less resilient through this proxy measure of diversity. This was led by some ecologists I had the privilege to work with, and ecologists argue about which richness measure and diversity measure is the appropriate one for good reason. And so we did it 3 different ways, and we had the same finding with 3 different diversity metrics. We drilled down into the size of trees. Size is not a perfect proxy for age, especially in urban areas, but we know that the large trees are not young, that it does take time to grow. So we looked at large trees in Roman numeral 2, trees that are greater than 20 inches in diameter at standard height. And what we find is that your odds of having a large tree are 9 times lower in a formerly redlined area than the A counterpart. So statistically significant larger street trees in Baltimore City in what used to be A or B than C or D. Focusing your attention on the right of the screen, Roman numeral 4, the small trees. This is the recent planting activity. We find statistically significantly more small, less than 5-inch trees in the degraded neighborhoods. There's a strong signal of city and nonprofit partners planting street trees in those areas that used to be degraded. So what does the future of the urban forest look like? Are we going to lose those large street trees in A? Is the inequity going to shift, and we're going to have more tree canopy cover from the street tree population in D than in A? Only time will tell. So thanks for the opportunity to share this research. I'll be available for questions and answer. And I just wanted to summarize, we know that redlining is a strong predictor of tree canopy cover. It also relates to species composition with street trees, at least in Baltimore. This is a platform to build other types of research because we've made the data freely available. If you have any questions, I would love if you could reach out. I'd be happy to share data, other resources, and to be as useful as possible. Thanks again for the invitation to share and for your attention.